Chapter 9.1 is going to be split into two different sections. First, we're going to focus on what we call sequences, and then we're going to look at series and some properties of that. The biggest objective here are to consider the comparisons of functions and sequences. What we kind of discovered in our activity is that we were dealing with what we were calling sequences, or these patterns, and what we were able to do is we were able to graph them or come up with equations for them. So we really used functions to help us with these sequences. What are the comparisons? What are the differences and similarities between the two? So we'll get to that. The other thing is we want to understand notation. The biggest part of these is sometimes you're going to see a sub 5 equals what? And that's just a way of me asking what is the fifth term in a sequence. So to just see something like a sub 5, you need to understand what is that notation, or what are these symbols trying to ask of me. That's sometimes the biggest thing to overcome in this study of sequences and series. Alright, so here's some key vocabulary. The first one is, of course, a sequence. This is the first one that we're going to tackle. What we're saying is we are just looking at a function. So we're trying to come up with an equation, right? Because a function is an equation where we know for every input there's only one output. But one thing is, those inputs, they have to be, so again, domain is just all possible inputs. What can you plug in? Well, if we're talking sequences, the only thing that you can plug in are going to be positive, and they have to be whole numbers. Okay, so that is the definition of a sequence. A term is just a number in a sequence. So when you're identifying that pattern, if I want you to find the fifth term, or like I did in the packet, 42nd term, would you be able to do that? That's all I'm asking, is down the line, what would that be? So here's that notation that I was talking about. A sub n is how we're going to identify some sort of sequence. So instead of using f of n, what we're specifically going to be doing is using a sub n to represent it. Okay, so yeah, we could have used f of n since we just said that a sequence is a function, but instead we're going to use this notation because it clearly signifies, hey, I'm starting to generate a pattern of numbers here, and we can only use whole numbers as inputs. N stands for then the position that that term is in. So if I wanted the fifth term, I'm going to let 5 be for that n. So instead of just leaving this open as a f of a of n, I want a sub 5, which would mean I would want the fifth term. So here's an example of using our notation. I've identified an equation for a certain sequence. So I'm identifying my sequence as this, and what I could do is I could generate a sub 1 from that equation, which again, had we just been using this notation, we would be saying, hey, my input, or the position I'm interested in this case is 1. So you would plug that in, you would get your first term. So this is another way of, instead of saying what is the first term, so what is the first term in my sequence, and then given this equation right here, what I can just write is, well, given this, what is a sub 1? That is what I'm asking. What is the first term? This right here, what is the first term? Okay, a sub 2, I would just plug that in. So again, I could have asked you what is the second term in the sequence, but instead I'm just asking you a sub 2. There that is. And you can see then that this is our set. This is what I would generate from the sequence up here, and it would go on forever. Alright, this might look familiar to you. I did have a problem like this, or this pattern, in one of the problems or the puzzles that you worked with. So the idea is, some of you came up with this whole idea that you have this length of our garden, and you could just say 2 times whatever that length was, and then add these 2 extra guys, right? So here would be 2 times 4, because you have the length, and you're going to need 2 of those lengths. So 2 times that 4 plus 2, because you had to add these extras. So one thing is, I want to bring this up. What if I looked at it like this and said, hey, we're going to start with these original columns. So this one right here, and then these ones right here. So the idea is those columns appear in every single one. It's something that they have in common from the gardens to come. So the idea is, we originally started out with 6, and what we're doing is we're adding 2 for every figure that we move down. So you could say 2 times n, because this was our first term, second term, third term, and so on and so forth. So if you would look down here is, hey, if I were to plug in 1 here, we would be at 8. So that's our point. And then same thing here. So here we kind of have a graph. Technically, again, if we were to write this as a sequence, we would not be able to connect a line to it. But the idea is those points do have a certain pattern, and it is a linear type of pattern. And we'll talk more about this linking to linear equations in the next section. For now, just know that sometimes these graphs can really help us kind of visualize what's going on. Alright, so here's another example. This is number 3 from your homework. So if I were to say a sub n equals 2 to the n, so find the first 5 terms of the sequence. Well, here we go. I would say the first term would be a sub 1. That would just be me simply saying, well, 2 to the 1. So here we have 2. A sub 2 would be, hey, they're saying plug in 2 for this nth term. I want the second term, so let's plug in 2 for n. Here we have 4. And if you start getting the hang of it and you can see kind of what is going on, you can go ahead and simply say, all right, a sub n is equal to, and then here I go, 2, 4, 8. And if you did get stuck, you could go ahead and continue on with this, but it's going to be 16 and then 32, ... They only asked for 5, so I'm going to end it at that. All right, one thing, we're going to highlight this more in the future, but we have what we call infinite sequences and then finite sequences. This last one, I only wanted the first 5, so I guess that would be something that was finite. But note that if you ever wanted to continue on, you can just put these ... and it's going to be something that's going to go on forever, that they can just assume, hey, this pattern is going to continue. If you did want to close it, you could always close it as well, or end it. All right. One more key vocab here is an explicit sequence. This is going to state terms. It's a way of notating so that you state the terms with respect to the term's position. So it's like what we've been dealing with in the last 2 slides. So here's another one. This is number 2 from your homework. If you had a sub n equals 5 times n minus 3, this is something that, hey, if I wanted like the 100th term, I could just go ahead and directly plug in, and then I would get my answer that I was looking for. So this would be 497, right? So it's something that's very explicit. You just sub in your position that you want, and you're going to get that term that I want, so that 100th terms. All right, recursive. Recursive sequence is a pattern in which previous terms are needed to find the next. It's also repetitive. I mean, this is very key, repetitive. This is something that once you identify, oh, I'm just adding 2 over and over again, you could always identify it as a recursive sequence. Okay, let's do an example of using this recursive sequence as we just have mentioned what it is. So now what I want you to see is what they're going to have to do is define a first term for you. So this is where they define a first term. So they're always going to have to at least define one term for you, so a starting point or some sort of place where to start. So there's our defining or our definition of a starting place. So then what I want you to notice here is if I wanted a sub 2, what they're saying is you're going to have to, in order to get the next, this plus 1 is indicating that you could take and get a next term. And note that they change n interchangeably. Sometimes they use j, sometimes they use k. Here they're using k. But still we're using, hey, if you wanted the kth term plus 1, so the next term, this makes us look at the next term, then you would have to use the one previous to it minus 4. So if I wanted a sub 1, what I would need to do, since my k plus 1 is equal to 2 here, so k plus 1 is technically equal to 2, then what we would have to acknowledge is that k, subtract 1, would just be equal to 1 here. So I'm going to be using 1. A sub 1 minus 4. And so that's why we need to start, because now what I can do is take a sub 2 is equal to 28 minus 4, which is equal to 24. So now I have my a sub 1, that was my start, it's 28. A sub 2 would have to be 24. And then a sub 3, what I would have to do for a sub 3 is take my a sub 2, 1 less, right? Here's the next one. Here's my next term, so I'd have to take the term previous to that. So a sub 2 minus 4, which would have been equal to 24 minus 4. So here I'm going to get 20. Again, once you identify what the heck that pattern is saying, go ahead and fill in your rest. And what I'm observing is, oh yeah, all this recursive statement is saying to me is subtract 4 from each term to the next. So you can see that happening right here. Okay, there's where that recursive or that repetitive step is coming into play. Okay, the last thing that you need to know is what a factorial is. So it seems a little out of place, and I would agree with you, but we do need to get in factorial. So this has to do with sequences as well, and you'll see why eventually. But it's notated by n exclamation mark or factorial is how we really read that in math. It's a factorial, actually, not an n, not like that. I'm not excited about n. The factorial of a non-negative integer, so keep in mind this n has to be non-negative. We have to be something that's non-negative. All right, and what we do is the product of all positive integers, so again, integers is just whole numbers less than or equal to n. So an example of this, 5 factorial would be, again, 5 fits that limitation that it can't be negative, and what we would do, all positive integers less than or equal to n multiplied. It's the product of those. So there you can see how that works. Find factorial on your calculator. If not, then I will help you tomorrow in class. And then evaluating factorials. So here for number 63, what I am going to write this out as is 4 times 3 times 2 times 1. And I know this is a little confusing because I don't have them on top of each other, but this is just a fraction. Okay, and then on the bottom here we have 6 times 5 times 4 times 3 times 2 times 1. What I want you to see is I use these definitions to the fullest, but now these are going to cancel out, these are going to cancel out, right? So we just have 4 is reduced to 1, 3's are reduced to 1, that's what I mean by cancel out, and then so what we really have is 1 on the top, and then 6 times 5, which is 30. There we have it. All right, here, this one's a little tricky. So if we had n plus 2, let's go ahead and try something. If you don't see what exactly is going on, then let's go ahead and try actually putting numbers in this. Let's try n equals 4, shall we? So if you had 4 plus 2, that's the same thing as 6 factorial, right? So 4 plus 2 factorial, and then we had 4 factorial. What this is going to be then is 6 times 5 times 4 times 3 times 2 times 1 all over 4 times 3, and I'm not even going to down to 1. Those canceled each other off. So what I would have is that 6 times 5, so equals 30, right? Let's try another one just to kind of see what's going on. Let's try n equals 5. So what we would have is 7 over 5, right? So what I want you to see is as we play this out, I'm not even going to dot 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 all the way down to 1. So then here, 5 times 4 times dot 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 all the way to 1. Again, these are going to reduce down to just 1, 1. So now we're going to get 7 times 6. Do you see a pattern? Do you see something that's happening here? If not, keep playing with that, and then we'll discuss what is your final, what are you going to say for your final answer here? If I had 8 factorial over 6 factorial, this is just going to be 8 times, and I'm going to start to get lazy here because I know something's going to happen. Dot 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 down to 1. All over 6 times dot 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 down to 1. Those are going to reduce. I have 8 times 7. What's going on? What should I say that this is equal to? Your homework is right there. We will have Wednesday to work on that, or tomorrow to work on that. You also have 9.1 part 2 that you're going to want to watch a video. We'll work on that all together on Wednesday.